In this podcast, I talked to my friend Marino Duran, who most recently was a senior cloud engineer for a company called Ping Identity. We started our discussion with the question, if programming languages are interfaces to computers, why is it that those interfaces are language-like? And we talk about language and abstraction and some computer engineering. So if that sounds interesting to you, you're welcome to join us. Can I tell you about what I'm working on and then get your help sorting it out?
Yeah, I'll try my best. It's been a while since I was in the Python realm, but
I'm not too specifically focused on Python, and I've had your voice in my head lately. Well, really, just as I was like preparing for this call and waiting for you to jump on. You told me before that when you were trying to solve a math problem, your first step was understanding the form of the answer, and I might need your help with that too.
okay.
Even before we dig into it, I just need some like maybe problem solving help and question defining help, and then maybe answering the question help. So I've been thinking about programming languages and why they are what they are. And I think it's true to say that a programming language is best understood as an interface to a machine. And you could maybe more specifically say a programming language is a language-like interface to a virtual machine or a digital machine. I know virtual machine has like a specific meaning, but the machine that you're interacting with the programming language is not exactly the computer hardware. It's something that's built on top of and hosted by the computer hardware. And the question that I've been stuck on is, why are these kinds of interfaces language-like? As I've been thinking about it, I thought a machine offers a certain amount of potential to do some function or functions. Like I have a Keurig in my kitchen and it will make 1 cup of coffee. That's what the machine is designed to do. It doesn't allow me to specify the size of the cup of coffee. It makes 1 cup of coffee. It has one button on top. When I hit that button, it makes a cup of coffee. And if I want to modify the volume, I pour more water or less water into the reservoir in the back of the machine.
Mm-hmm.
And I change the flavor by inserting a different pod into its compartment. So you could say that my Keurig accepts 2 arguments and it has one function. The function is make 1 cup of coffee, and it's got one button for that. So it has a simple user interface. On the other extreme of the spectrum, you have something like an airplane cockpit that has knobs and buttons all over. That machine, the airplane, offers a lot of potential for manipulation, many different functions. And so it has a complex interface to allow me to manipulate the machine to do what I want in different ways. So it offers more potential than the Keurig, if I can use that word. I don't know if potential is the word that I've been using to describe this characteristic. If you think of another word that would be a better name for this thing that I'm trying to point to, then like let me know.
Mm-hmm.
But at first I was thinking there's a relationship between the potential offered by the machine and the complexity of its interface. Like the more potential the machine offers, like meaning the greater variety of functions that it can perform and the greater ability to modify those functions it allows you, the more complex its interface has to be. And I think maybe that is true. Maybe that is right. And then I'm also thinking that if you go all the way down to the lowest level of a computer, down to the hardware, that hardware offers massive potential. And the point of the machine is to process logical operations. Like a computer is a logical operation processing machine.
Mm-hmm.
And so you start with logic circuits, and then you can combine those into like memory cells and other things. And so you're combining logic at the smallest, simplest level into machines like logic machines that perform more complex tasks. You interface with that hardware through the CPU. Virtual machines or digital machines are built on top of that, such as the C, maybe it would be right to say like the C compiler or the Python interpreter would be the machine. And then the Python programming language would be the interface to that machine. But then I can also build applications like PowerPoint that do not provide a language-like interface. They provide an interface I can interact with my mouse.
Mm-hmm.
It's more like a mechanical interface like my Keurig, or kind of like the cockpit, but a simplified version. You know, it has so many buttons that I can press. So what I'm trying to figure out is, why is it that programming languages, like that the solution for the interface is to make it language-like at that level? Does that make sense? In other words, like it's not a cockpit. Are you familiar with the ENIAC? It was a computer that was created in World War II It was used to perform some calculations during the development of the hydrogen bomb. It filled up a room, and it was programmed by plugging and unplugging wires to a plug board and then flipping switches. There were like thousands of wires and switches.
Mhm.
And it would take the people who were running this machine days to reconfigure the wires so that the computer could run a new program. And it was using something like less than a kilobyte of memory. So much less sophisticated than the computers that we use today. And it would take them days to reconfigure that thing, like with the cockpit equivalent interface, where you're moving things with your hands. And so we've abstracted away from that. And so I'm trying to figure out, like, why is the solution something that resembles a language?
Oh, that's a good question. I haven't thought of this question, but hearing you talk about the different programming languages, we know that you have all of these layers, and for all intents and purposes, they're abstractions, right? We do not need to occupy ourselves with the management of memory when we're
Mm-hmm.
trying to produce something, in the very same way that someone who needs to create a PowerPoint doesn't need to learn a programming language, right?
Mm-hmm.
The
Like the
span,
passenger on a plane they don't need to know how to operate the plane. They just need to know how to buy the ticket.
right? And so if that gets you your goal, then we don't want to bog you down with all these other complexities, right?
Mm-hmm.
And so when you look at different programming languages, the reason why different programming languages exist is because the syntax, the writing of that language makes it easy for you to achieve your outcome without the complexity of things. So,
It's
for
just the right
example,
level of complexity.
it's just the right level of
Or maybe you
complexity.
could say the right level of potential also.
Yeah, so I think of like you have a machine that has a certain amount of potential, right? Utilizing like so that's like the ideal of it. And then you have these programming languages that can never achieve the full potential, but utilize it in different ways. And so if you think about like C++ and Python, if I need to write a program that parses something, I'm more worried about parsing strings of sentences, maybe manipulating it, maybe separating it, and things like that. I don't care about the memory utilization of different letters. How do I store that and all those different things. So if I'm writing a programming language, I would want a language that allows me to, I just need this and I need to convert it into that. And if I use C++, I have to take into account the memory of each letter, stringing them, what a space looks like in memory. You know, if I parse something, then I have to delete that memory. Otherwise, I'll just keep adding that. I can fill up my entire memory. And so it has all these complexities, and you're just like, this sucks for me to achieve this. But if
But
you're
that has to be dealt with at some point, because that data does have to be stored in memory somewhere. So at some
right,
point, somebody has to solve that problem.
yeah, and someone did, and it comes at a cost. And so the person who's writing a program for controlling an airplane needs to use the C or C++ because they're processing signals from these knobs and these buttons, and they need that granular like look, versus Python won't do that because Python tends to abstract things.
Mm-hmm.
And so Python, what gave it a simplicity is that someone did solve the problem. Someone wrote code that says, don't worry about memory, I'll handle it, but at the expense of efficiency. So while your code is running, there's other code that's running that is looking at the data that's being processed and saying, hey, you're not using this anymore. I don't see that you'll use it in the future. I'm
Mm-hmm.
going to get rid of this, right? And it's doing all of that stuff because it's been abstracted. Now you don't have access into that abstraction,
Mm-hmm.
right? The
Which maybe I
virtual,
didn't need, but if I ever did, I couldn't access it through Python. I'd have to go down into the C.
right? You would have to use a language like C. So it's really about like I guess the granular details of the problem you're trying to solve. And so that's what I think about when there's different programming languages. So when you look at a program, anytime you learn a new programming language, it takes you a while, but then at some point you're like, oh, I get it. I know what this programming language makes easy.
Hmm.
I can create this
Oh,
thing super easily. Like if I'm doing a website and I'm on there, and then I'm running JavaScript where I can just in 2 lines I can create a box and put something in it. It's like for me to do that in C++, oh my gosh, right? I have to, well, what's the dimension of my screen? And okay, then I'm gonna do one box and then another box, and you're writing all this information down is so time consuming and all that. Versus in
Mhm.
JavaScript, it already has pre-built functions that can create that for you because there's these
Mhm.
patterns and it abstracts things that you don't care about and stuff like that.
It's like if I'm building something out of wood, I could use a screwdriver to like screw all my screws in, or I could go and get a drill, which is made for this, and it just makes my job easier. I have a machine that does that labor for me. I can't think of a case where I'd be building something with wood where like I need the granular control of the screwdriver. So maybe that's not a perfect example.
Yeah, well, if you have something maybe miniature, that the lowest setting of the torque of the drill would break it,
Uh-huh.
and you can't use the drill for that. So you
Yeah.
need the small screwdriver where you need to have that pressure where you do it yourself, right? And it's like one is fast and gets it done, but it's not applicable to this other thing you're trying to build. And so you need a
Mm-hmm.
different set of tools. And
Mm-hmm.
they're both used to build, but they're different.
Okay, so we've addressed the layers of abstraction.
Hmm.
We gain efficiency by abstracting away from the granular details.
Hmm.
And the cost of that efficiency is potential or customization, would be different ways to say it. Maybe I don't need that. But that still doesn't quite answer the question, why is it a language like interface? Because there are examples of layers of abstraction all around us. Like the one that I'm beginning to like the most is I can go to a restaurant, like, down in Austin or up in Dallas. There are Tex-Mex restaurants that serve burritos. So, like, let's say that there's a restaurant and they only serve two kinds of burritos, chicken burrito and a steak burrito. I get to make my choice. If I don't want one of those things, I don't go to that restaurant.
Hmm.
I go to a different restaurant, and maybe they'll allow me to make some small modifications. It's like I don't want beans on this one, or I'd like some extra rice on this one, but they're not going to let me recreate the burrito. However, I can go to Chipotle and they allow me a lower level of control over the construction of my burrito. I go in and like I get that they have all of these ingredients like components, but none of them are assembled into a dish. It's like, do I want a tortilla or do I want a bowl? Okay, I want a tortilla. What do you want to put in it? Okay, chicken, black beans or pinto beans, black beans, brown rice or ripe. I get to construct the whole thing from its components. But then Chipotle only offers me this limited array of ingredients. I couldn't make pumpkin pie out of the ingredients Chipotle offers me. If I want to do that, I need to go to the grocery store. And the grocery store offers me a much larger array of ingredients. And in fact, I could still make a burrito out of the ingredients that I find at the grocery store. Maybe Chipotle's beans are too salty, but when I'm going through the line, I can't say, could you give me black beans with less salt? It's like, we've already cooked it. We've prepared this in the way that works for most people, kind of like
Right,
the drill. Like the point of this restaurant is not to satisfy your edge case.
right.
You need to go to the grocery store for that. Then you can get your own beans and you can get your own salt and you can cook it and, assemble it in the way that you want. But then even the grocery store is a curation of the ingredients that I can buy across the world. Like maybe the grocery store doesn't have exactly the kind of beans that I want, and I can go source them from like South Carolina instead of Mexico or whatever. But when most people want lunch, they're not thinking, are these South Carolinian or Mexican beans? They want to go to the restaurant and say, I want a chicken burrito, or maybe they want to say, I'd like a burrito bowl with like X, Y, and Z. And I guess when I go to the grocery store, I'm not interfacing with these options using language. I'm interfacing with my body. Like I walk into the store, and if I'm going to get just a couple of things, I can use my hands. If I'm going to get a medium amount of things, I can use one of those small baskets. If I need a bunch of things, I'm going to get a big push cart. And then I navigate the store with my body and I choose the ingredients that I want with my body. I put them into the basket, and maybe I go through the self checkout and I like scan them with my body. I might not have to talk to anybody at any point. But even Python is more like the grocery store than even Chipotle, because it does offer you so many options and so much potential for modifying the way that functions are executed.
I would argue that the grocery store is C++, and the restaurant that has the chicken and burrito is Python.
You think they're that far apart?
Not that far apart, but if we're categorizing them and breaking them up, and we're saying, because like if I want a chicken burrito, I could go to that restaurant and get a chicken burrito. I could also go to the grocery store, but there's a lot more work that I'm going to have to do at the grocery store to
Hmm.
get the chicken burrito, right? I can just say two words and get the chicken burrito, which in Python, you can just say, like, this function, here's the parameter, give me back this. Versus in C++, you have to say, okay, I'm going to create a function. I need you to allocate this much memory. This is the kind of data that I'm going to give you. And then when you get that data, this is what I want you to do with it, and so on and so forth. And so in terms of complexity, the grocery store with all of its options is C++ with all of its options. And then Python is a more simple thing that it abstracts everything, right? And so if you want that easy, I'm just here for this, you just do it. So you can
But
say,
what
I,
about like Chipotle though? Would you say Python's more like Chipotle, where it gives
or
you an
like,
array of ingredients, and then if you want, you can pass an argument like, "Can you give me extra beans?" But you can't say, "Can you give me less salty beans?"
yeah, so if we're making a direct like example between the example of the restaurant and the programming languages, then yes, Chipotle would be like Python, and the grocery store would be like C++. But what I'm saying is the comparison of a grocery store to the restaurant that gives you the beef or chicken, that comparison then can be compared to the difference between C++ and Python in terms of the granular options that it gives you, not them indirectly. I'm talking about their differences. But if we were to map them, then 100% Python is like Chipotle, because you can just say, I can create all these different things. I don't care what kind of beans these are. I don't care
Hmm.
how much salt is in them or anything like that. Versus you can say, I want you to allocate this memory space, and I'm only going to put a Boolean value in here, which is I want the beans with a little bit of salt, kind of a thing. And then I think you were kind of moving into the direction of saying, well, like when I go to the grocery store, I don't need to use language. I can just physically go in there and do the things. But then also, your end product is a physical thing. And I think in programming,
Hmm.
your end product is data,
Good point.
right? So I think physical with the physical, but then data and insight has to do with information. There's something between data, information, and language, right?
Yeah, yeah, okay. I think you're getting at something. So you're saying I can get by navigating the grocery store, selecting my ingredients and cooking them without language because I'm producing a physical product. But I think you're getting at something, but the ENIAC was physically manipulated. So it's possible to have a physical control even for manipulating data. It's just to have a physical control for something as complex as this,
Right.
as
Yeah.
opposed to
Right.
the ENIAC, it would be so huge that it
Right.
would be impractical. And so somehow it's like language and abstraction work together.
Together.
Like
Right.
there's some kind of course. Well, and it kind of makes sense. There's some kind of correspondence between language and abstraction because language is abstraction. Like
Hmm.
Larry Arnn says in his Aristotle course, Ethics, he mentions, and he likes to say it elsewhere too, that common nouns are categories: dog, cat, fork, house,
Mm. Hmm.
man, woman.
Mm.
None of these are individual, specific, particular instances. Hey, Marino, can you grab me a pen? Which one? Doesn't matter. That's an abstraction.
Yeah.
Like, I'm not telling you, could you please go grab that specific black pen with your index finger and your thumb and take 3 steps back here? It's like, I don't need to
Hmm.
do that. So,
But you can.
and that's related too. So, like,
Yes.
language works at different levels of abstraction. Like,
Yes.
it's not,
It
it's
allows
not
you to
less
pierce through.
effective at any
Right.
one
At any one
layer of
level.
abstraction.
Yeah, I just so when you were talking about how you can physically go in and you can achieve getting this burrito just with your body, it's like, well, I can communicate with just sign language, right? But let me try to read maps of meaning to you using sign language, right? Good luck to me for that. It's going to be very challenging. So like the physicality of it, as opposed to using language, the language allows us to get to that like high level, not I'm sorry, not high level, high resolution of details.
Well, and so when you say sign language at the grocery store, do you mean like just rudimentary gestures?
No, I mean, so let me go back. You were saying that we can still program through manipulation of mechanical something, right? Because
Yeah.
at the end of the day, the electrical signal is a physical thing that's
Mm-hmm.
happening, right?
Mm-hmm.
And so you're saying, well, we could still mechanically talk about information and data, and we can. And the very same way that I can use sign language to communicate ideas and data to you. However, just like trying to, what was the name of that computer?
The ENIAC?
The ENIAC, just like having the ENIAC do what our iPhones can do now, it would be a real challenge. It would be this huge machine. It would consume all this power. Honestly, it might not even be possible because the complexity is exponential, right? And so if something isn't working, how do you find that something? And then in that process, you everything, and then you completely lose track of the entire system.
Yeah, how do you debug the plug
Yeah,
board?
right. You don't, right? And so then I was kind of overlaying that with the idea of, well, I could also communicate to you using sign language. But then you look at something like Dr. Jordan Peterson's Maps of Meaning,
Which
and
is
then I
relatively abstract. Is that your point?
it was relatively abstract, and it's dense, and there
Uh-huh.
are words in there that are not, that there's no single gesture for, right? These words are, they have a history, they come from Latin, there's all of this stuff, right? And so then it begins to kind of fall off, and the only thing really that gets us there is language.
Okay, so then could we say this might not be exactly right, but language is abstraction agnostic? Like language is equally as effective at any meaningful level of abstraction. Like as long as whatever's happening at that level of abstraction is meaningful, we can name it and speak about it no less precisely, no less effectively than at the most concrete level of communication.
I would say so, at least as far as we know. I think that the ultimate ideal abstraction is in our minds. And I think just like the computer is the hardware, our language is what accesses that potential in the very same way that a programming language accesses hardware.
Could you say that one more time?
I would say that in the very same way that a language accesses hardware, language accesses our mind, which is hardware. Language can pierce any level of abstraction, and as long as it has any meaning, then language can get there. But the abstraction is actually in our minds, right? It's actually thought. Our meaning is in our mind. It's not out there. And
Because
so
out there, like you could describe Python and the hardware in physical terms equally. Like you could create a material description of both of these things, even though when we speak about them, we say Python is more abstract than the hardware. Like you could describe Python as electrical impulses stored in memory,
mhm,
like binary signs
mhm.
stored in memory, just as well as you can talk about the operating system stored in memory. Like physically, they both have a physical material representation, even though we say that one is more abstract than the other. Is that what you're getting at?
No,
No? Okay.
I was actually trying to understand what you were saying, which led me to believe it wasn't what I was saying because I
Okay.
would have understood it. So we have an abstract concept idea, something that has meaning. We use language to articulate what that is, and we can move through layers of abstraction because our language allows us to do that, all the way from vague to all the way to highly refined, specific. This is the meaning I am speaking about. And I'm saying, in the very same way that language allows us to achieve the description of that abstraction, would be the same way in which a programming language is able to utilize the full potential of hardware.
You're saying the same way that our language allows us to represent abstraction, that's the same as the way a programming language allows us to actualize the potential of hardware. Okay, I think I'm understanding what you're saying. So I have some meaning. I have something that I perceive pre-verbally, and I want to communicate it to you. And so I actualize a representation of my meaning, in language. And
Mm-hmm.
language allows me to do that perfectly well.
Mm-hmm.
I'm not, I can express pretty much anything I can think, no matter how abstract it is, with precision. The hardware has potential before you actualize it, but the software, it arranges that potential according to an idea also. I mean, it doesn't do it by itself. There's some engineer, some developer who kind of like I said pre-verbally, I have some meaning. It's like pre-coding, whatever you want to call that. Like he's got an idea of something to create, and then he expresses that in code.
Mm-hmm.
But that code, it doesn't merely represent the idea, it actualizes the idea through the hardware.
Through the hardware.
But there's a
Right.
relationship between those two things. They're similar.
I think so. Because I'm kind of aiming in the direction of like, well, why are we using language as a programming language and not something else? And then if I said, well, if we are hardware, why do we use language to communicate?
I don't think I mean, we are obviously to some degree. I mean, it's like I have biological hardware.
Yeah,
I mean,
that's
every
what I'm
part of me.
referring to. That's what I'm referring to.
But there's something else going on too. Like we had this conversation in Austin once. Like you're really in there. You are in there hearing my voice right now, understanding what I'm saying, having an experience. Me too. That's not the case with the computer. And
No.
so when I write code and I execute it, the computer doesn't understand what I mean any more than my keyboard understands what I'm typing when I'm pressing buttons.
Mm-hmm.
It's mechanical. I mean, like when I execute code, I am catalyzing a sequence of physical events that cascade through the
Mm-hmm.
circuitry of my computer. And it just so happens that the circuitry of my computer is designed to produce a
Produce.
meaningful output, which is amazing that we can produce like physical representations of logical operations that produce the right answers. Like
Mm-hmm.
that's a profound fact of reality, but that doesn't mean that the computer is understanding me. And so it's not exactly that I'm communicating to it. I'm manipulating it the same way that I would manipulate the strings on my guitar.
Mm-hmm.
Like I'm pushing it down with force and I'm making it vibrate at a different frequency. I'm not asking it to vibrate at a different frequency, but we represent these physical catalysts with language by associating like the name of a function, for example, like the print function. That function is implemented in C, and the Python developers they program into the Python interpreter that this function is initiated by the characters print with the syntax, with an argument in the parentheses. But they could have any arbitrary sequence of characters could have been assigned as the catalyst of that
Yeah, and
function.
in other programming languages, they're different.
Uh-huh. Yeah, right.
They're PR.
So the communication, like the meaningful communication that's happening is between the developer who created the function, like the print function, and the user who's using that function in their code. So they didn't choose an arbitrary sequence. They chose a meaningful word
Mm-hmm.
in English. The computer doesn't know the difference. The user knows the difference. So it's like
Right.
I'm putting a label on top of a part of a machine, like the microwave. I've got a button on the microwave that says cook time. I've got another button that says kitchen timer. One of those buttons causes the microwave to cook. The other button only sets a timer.
Mm-hmm.
The microwave doesn't know the meaning of the words, the
Mm-mm.
labels.
Yeah.
I know. And so the creator of the microwave who labeled those buttons is communicating to me. And
Mm-hmm.
then I'm pressing the button with the meaningful label, but I'm initiating a physical sequence, like a sequence of physical consequences by pushing the button. I'm not speaking to the microwave.
But I guess then what this made me think of was the relationship between us and solving problems. Because language allows us the full spectrum of intricacy of describing what we're trying to do. And so now we have this highly refined mechanism that we can utilize as a tool to solve a problem. If we didn't, it would be a lot more difficult to solve problems.
Well,
And
you'd
when
have
you
to do it
look,
all in your head, right?
yeah, but even when you physically produce it, there would be a lot more of it.
What do you
And
mean?
so when you look at, for example, like if you think about logical gates, right? Kind of going back to those logical operators, there are many different types. We have or, and, nor, NAND, right?
Mm-hmm.
If we didn't have as many, let's say we had half of them, we can probably still produce the same outcome, but we would need a lot more circuits to produce that same outcome. Does that make sense?
I think what you're saying is the variety of
Mm-hmm.
circuits, which are analogous to like variety of expression,
Mm-hmm.
allows us to achieve a goal more efficiently. Well, I experienced this when I was down in South America. My Spanish is terrible. I know, well, when I first landed in Chile, I knew zero, like hola. But I had to learn because I had to get food and I had to tell my cab driver where to take me. And so I picked up enough that like after a couple of weeks of immersion, like I could talk to people. But when I wanted to say something, I had to find these like creative, awkward ways of using the limited vocabulary I had to like
Mm-hmm.
point badly to the thing I was trying to say. And like they would get it, but I had to take the long way around.
Yeah.
You're saying like that our verbal vocabulary and our technical vocabulary are kind of similar, like a more specialized vocabulary lets you get straight to the point.
Yeah, I think when problems are abstract, they're difficult. Depending on what you're using, what tools, what mechanism, it can be very difficult to solve a very simple problem. Case in point, those challenges that they give children where they give them straws and tape and paper and string, and they like create a mechanism that doesn't allow this egg to break if I throw it out of a two-story building, right? If you had all of the material in the world to solve this problem, it would be easy, right? You would design something that, will protect the egg 100% of the time.
Mm-hmm.
It becomes a challenge when you have a certain limited set of materials to achieve that. If we look at the kinds of problems that software solves, as soon as we enter the realm of data, we're pretty much exposed to all of the problems, right? We're after solving a simple problem, but then we run into the problem of representing that information in such a way where we can solve it. And
Could
then
you say
that
that one
just,
more time, please?
how far do you want me to go back?
You were talking about representing data.
Yeah, so we begin with this super cool concept that we can arrange physical circuits in a way that they can produce electrical signals that allows us to represent information.
Mm-hmm.
And then we say, well, if we can represent information and manipulate it, then I can represent a problem and manipulate it, find the answer, and then represent that back to me and
Uh-huh.
have the solution.
It works.
And it works. Kind of like Fourier, Laplace.
Yes. I was thinking about that as you were saying it. I didn't remember the name, but it's like, yeah, you put it into this magical thing and it comes back
Yeah,
and it's
and it
right.
comes back, right? So, yeah, Fourier was like, wait a minute. In this realm, I can manipulate things and solve them and kind of just bring them out. And so that's kind of what I was trying to define there and articulate there. And so I think in that pursuit, then we very quickly just realize kind of the scope of things, where it's like, okay, I'm trying to solve this problem, then I run into this other problem. It's like, how am I going to represent information? And in the representation of that information and in pursuit of solving the problem, once the information is represented, we run into all these other things. And I think in the construction of those systems, those mechanisms, we needed a way to have the
You said to what?
expressive variety. Hmm?
Part one more time.
What part?
You just broke up a second ago.
Oh, yeah, it's getting a little choppy. Um, I think in the endeavor of trying to solve the problem through this like mechanism, through this very abstract concept, we run into all of these other problems. And in our pursuit of solving them, I think naturally it just became evident that because they're so intricate, the only viable thing that could allow us to articulate in a way that allows us progress into solving these problems was through language. Someone decided this was just ones and zeros. At some point, someone said, if this string of ones and zeros, we all agree, says Marino, I don't want to look at this ones and zeros. I'm going to write something that's going to interpret this for me in English.
Mm-hmm.
Someone made that decision, and it could have been something else, and it wasn't.
Mm-hmm. So, like, I'm gonna create a data structure called a list. Like, it's useful to have a list of objects that are indexed so that I can pass an index to the list and receive the object at that position.
Yes, I think that is more of a specific, yeah, absolutely. But I think the point that I was making is that in the evolution of computers, right? When it first started with I can store a charge or an energy or something, right? And then I can have RAM, bytes, bits are just mini capacitors.
What can you remind me what a capacitor is?
A capacitor, the technical term is a dielectric, which is just two, I don't want to say two plates, but two materials um, that are electrically charged. And when the source of that charge is removed, it can still hold that charge.
Oh, okay. Yeah, so that's memory. Like
That's
the
memory,
presence of the charge is a one.
is a one, correct. And so you could just have, like on your desk, 24 capacitors. You have a 24-bit memory address,
Mm-hmm.
right? And so I got to the point where they were like, okay, we can kind of store these values here and we can represent that. We can all agree that like 11000011 is this letter or whatever the case is.
Mm-hmm.
And then they were like, okay, we
Which is an
can,
encoding standard.
right, turned into a coding standard. And I think that once we represented numbers and then we figured out using logical ands, ors, and all that, that we can do math, that's how we got to our first programs of just
Mm-hmm.
like, we're going to put these values of numbers, run these values of numbers through all of these, through an LLU or arithmetic logic unit that
Mm-hmm.
does all these operations, and then it gives us an answer back. And then we started building on that. But I think as we were doing all that, and it was getting very complicated, people were with wires and switches and all this whatever. Someone, and I don't think it was someone, I think it's like people were like, we need a better way. And that better
Yeah.
way ended up being language.
Looking into the history would be informative. I want to do that. I've been wanting to do it this week, but like I have to produce a video on this tonight, and so I haven't had time. I've been thinking about it for 3 weeks, but I haven't chosen not to dig into the history, even though like answers are surely there.
Because
I,
it not only was a decision, it was obviously the right decision. Look at where we are.
yeah, it
But
works.
yeah, but the point that I'm making is like, why did we choose to look at all those ones and zeros and say we need an interpreter and we need to use language to
Well,
organize this information?
I think I maybe have an idea.
Okay. Also, I don't know the answer to this. I'm loving this conversation and
Yeah, me too.
digging
And
through it.
man, like thank you for taking the time to do this with me. And it's fun to be able to do this with you again because we used to do this a lot.
Yeah. I don't have conversations like this
Hmm.
with many, and I kind of feel the uncomfortable of, when you first try to do something for the first time, or establish a habit where it feels unfamiliar. Even though
Uh-huh.
I used to do this all the time and I loved it, it feels
Mm-hmm.
unfamiliar. That's
Well,
interesting.
welcome back.
Uh,
Here's something interesting about reading a book. You can only read one word at a time. You have to read one word at a time, right?
well, one word has meaning, and maybe you can take two words and extract meaning. Two words can be one.
So you think about the context as you're reading, but
Hmm.
like you can only look at one new word at a time. And then maybe you hold them in your head and compare them together to interpret, to understand. But my point is, I can paint you a picture and present many things to you at once because my medium is two-dimensional. But writing, like written English, is one-dimensional. It's linear. Like one thing comes after the other in one dimension.
Hmm.
That is a highly constrained medium of communication. And yet we can say anything we want.
Hmm.
Like, what can you not communicate in a book? You can say almost anything linearly. So, but you can speak about the whole universe. I mean, it's the most hyperdimensional thing there is. And you can compress all of that
Right.
into, like, you can encode it
Hmm.
in linear form, and that is decodable by a reader into this like hyperdimensional object that you're trying to convey.
I don't think we have a valid understanding of the compressibility or the capability of encoding. In the same way, when we had that conversation, and I said, you can take a DVD and you can write onto that DVD every song that has ever been made or that ever will be made. You remember
Because
when we had that conversation? Because if you look at the amount of bits that you can fit a song, and when you look at it, is just a string of ones and zeros.
Mm-hmm.
Every song that you could possibly think of is just a different combination of ones and zeros.
Mm-hmm.
There are enough of spaces of bits on a DVD for you to fit every possible combination of these ones and zeros because of the length, right? And so you can encode every song that's ever existed or ever will exist onto DVD. And so that made me think of what you said of I can
Mm-hmm.
encode anything in the universe into this linear process.
Linear. Well, and it's not only linear, but binary. It's a linear string of two values.
Yeah.
What?
Yeah.
Like, that's so, like, does that mean you can encode any information in a linear string of binary digits?
Yes.
So that there's no limit. All you need is distinction. I mean, what is a 1 and a 0?
1 0.
It's just a difference.
Difference. Yeah.
Like it can't be a sequence of things that are exactly the same.
Yeah. And every medium of memory is just a mechanism that stores things in a distinctive way.
Distinction. That's
Distinction,
it. You just need one distinction. And then by modifying the pattern
Sure.
of distinction in a series of distinctions, you can encode anything?
Anything. Yes. Fuck. Yeah.
What does that mean?
Yeah.
That's-
That sums up your personality right there. What does that mean?
That's
crazy.
That's true.
That's crazy. It's insane. Yeah.
And so then, okay, what do I do with that? So I can represent anything using a series of bits. Well, when I do that with circuits, not only can I represent anything, but I can also transform that thing. Like I can design a process of transformation. Why? Because I can represent the process of transformation in bits too.
In bits too, yeah.
Because I can represent anything in bits.
Yeah.
And so the point of a computer, it seems to me, is to process logical operations. So step number one, you represent the logical operation, which means representing operands and operators. That's it, right? So I have objects, and then I have their relationships with one another, transformations relative to one another, like 1 plus 3. 1, okay, I can represent that. Increment, I can represent that process. 3, I can represent that. So increment 1 by 3, and like the computer will give me 4. And like, yeah, that's right.
And the computer, the hardware, is a mechanism that physically creates that distinction, that changes things between those two binary or those two distinctions, translates one distinction into another. It's a physical mechanism that's capable of doing that.
Mm-hmm. And the transistor is important. But that's a question that is probably beyond the scope of our conversation today, but it's one that I want to answer eventually. Like,
it's one of my favorite things ever, and one of the reasons why I actually loved being an engineer is once I understood the transistor.
Well, how much time do you have?
I don't. Today I've spoken to so many people today. I can give you a high level. We don't have to.
How about we save it for another time and do it again?
Okay. Yeah.
Okay.
Yeah.
Okay.
Yeah,
let's do it though, because I've been wondering about that for like a year.
Yeah, so that was a mind-blowing thing for me because I remember studying the IBM computer and all of the vacuum tubes.
Uh-huh.
All right.
Which accomplished the same purpose.
Yeah, in a very inefficient, terrible, shitty way. And then we were able to achieve what we're trying to achieve in such an efficient, accurate, redundant, persistent way. And it changed everything. And I remember that just coming up over and over and over. I'm like, what is this? Why is it such a big deal? And then when I learned, I was like, I just saw computers different. I was like, well,
it seems to me like gold. Gold is interesting because it is chemically incorruptible. Like the alchemists loved gold. They called it the virtuous, what did they call it? The virtuous chemical or something like that, because it didn't bond with anything. And so it remains pure, like it doesn't rust. That's a real thing that exists in this reality. Like there is a structure that a chemical can have that causes it to remain pure. And it's also useful. Like it's a good conductor, and its conductive ability is related to its chemical structure. So And because gold is incorruptible, well, it also happens to be beautiful, which is interesting.
I find that to be the most interesting.
And so we have these beautiful incorruptible things that we turn into our currency. It's like we represent value itself using this matter that is, it's incorruptible, because that's where you want to store your value. But it's like you could have used anything, but we picked gold. Gold is
The
the thing.
gold. Yeah.
It's like that's meaning embodied in chemistry.
Hmm.
And it seems to me like the transistor is kind of like that, because I mean, just from afar, like not understanding it, because it allows the production of this distinction. And that distinction is the only thing that you need in series to represent anything that
Yeah.
exists.
And if you take a step back and you think about, okay, we can represent everything in distinctions between two things. I think coming across, not even coming across, designing, creating something that I don't know what to call it. I don't know. It's not a translation. It's the process of changing one thing to another to create that distinction.
The process of changing one thing into another. Well, I probably understand what you mean better when you tell me what transistors are.
Yeah, but I just mean in terms of like even outside of that, thinking about we have these two things that are distinct from one another. Any mechanism that alters one into the other, what do you call that one into the other? That flips the
Transformer,
distinction. It
converter.
transforms it into the other kind of what it is,
Huh.
I suppose.
Like lead into gold.
Yeah, yeah. I'm trying to think of what I'm trying to communicate. We know that we can't store all information in a distinction in a series of, or a pattern of distinctions.
Wow.
And which is very interesting. But I guess my thing is, what do we call the transformation of what collapses that distinction, right?
What collapses the distinction?
Yeah.
Well, that seems like two different questions.
Yeah, I don't think that was.
Is it? Or like,
No, it is. That's different.
Did you not say exactly what you meant?
No. No, yeah, I didn't.
Okay.
What the thing gets transformed into the other thing, right? Because it could be anything. I could
Like light into
literally,
dark, or
you're right. Yeah, I
life
could
into death.
yeah, I could write you. I can go buy Pepsi and Coke, and use a series of Pepsis and Cokes to communicate a message to you, right?
Mm-hmm.
To
Mm-hmm.
solve a problem, to write
Mm-hmm.
a math equation, to anything, to write
Anything.
a song, in the very same way that a work of art, because you can also paint a painting with just black and white.
Mm-hmm. Yeah, which is just distinction. Well,
That's
even
distinction.
I can write you a letter. What am I doing? I'm taking ink. Like, what is that? All I'm using is distinction, ink and paper. Like, here the ink is,
Because
there it is
there's
not, and I can say anything that I want to you.
Yeah.
The thing that's most relevant to the question I was originally asking that I've learned in this conversation is language is abstraction agnostic. And maybe I'll think of a better way to say that, but it does not lose its efficacy at any level of abstraction as long as it's representing something real.
Yeah, it also has the ability to do so. Not many things do have the ability to move through, I guess, layers of abstraction. Some things, they fall apart at a certain level, like sign language. There's some concepts that are just, sign language is insufficient to really break down. Like let's say you're trying to solve the problem of helping people through therapy, and you can only use sign language. Like you'd probably not be effective at solving the problems that people have in terms of mental health through that.
Are you sure about that?
Well, maybe theoretically you can.
Because the reason I ask is because if you can encode anything in bits, then why not?
Yeah. So we could pursue solving that problem with literally writing ones and zeros, right? But that's such a surmountable problem or task to solve the problem in. So I guess if we're talking about just like theoretically, we can, because we can communicate anything. But I tend to believe we instinctively, we have the just propensity of utilizing the thing that works best. And even if it's not initially the thing that works best, ultimately we arrive at the thing that works best.
Mm-hmm. And it sticks.
But
And like you said, like there's something to the language thing because it works.
it works, yeah. And yeah, it has been working. It's working. Ooh, this is interesting. I just had an interesting thought. In the very same way that, let's say we did use sign language to solve mental health issues. Like maybe in the beginning we would make progress and it would be good, right? It wouldn't be
And
great or
so
as effective.
when you say sign language, I just want to make sure I'm understanding. Are you talking about like you and me, like I've lost my tongue and I'm just trying to gesture to you, uh, like in a rudimentary way, or do you mean like the American Sign Language system?
The American Sign Language system.
Okay.
Yeah. Which is just more refined of us kind of making gestures to one another, right? It's got just more agreed upon things, and so maybe it just encodes a series of things I otherwise would have been doing with one gesture, right?
Yeah.
And so if we did do that, maybe we could make progress, but it wouldn't be the most efficient way to do that, right? And it would be hard. And as we were trying to solve that problem better, it would just get harder and harder.
I think that you're getting at a point, and I think my argument is maybe not like exactly germane to your point. And so I'm sorry if I'm just ruining your illustration and being annoying, but it seems like the way that we solve this same problem with verbal language, like spoken language, is when it takes me too long to explain something using language at a lower level, I create a abstraction to make the point that I was trying to make with all those lower level words. And so it's like maybe, well, this is language. This is the way that language works. Like we begin with concrete things. Like here's a rock. And like I can go to you, caveman Zach and caveman Marino. I can go to you and I can go, huh, huh. And you're like, yeah, like,
Yeah.
huh. Okay, so now you get it. That's what this is. And then there's like a tiger. I'm like, ha, ha. You're like, ah. Okay, so we've got that down now. I can say, huh, and you'll hand me a rock. I'll go, ah, and you'll throw it at the tiger. But it's not enough for me to say, you've been a good friend to me, Marino. Thank you for saving my life. I feel gratitude toward you. It's
Mm-hmm.
like, that's
That's more
too
of a fist
abstract.
pump.
Yeah. But I'll say this is how it works. Jordan Peterson says when we learn, like the way that we learn is first I have a novel experience, then I dream about it, then I act it out dramatically, and then I can articulate it using language, which is to say, then I understand it abstractly. And so you have a child, they experience their parents, then they dream. I mean, they imagine maybe while they're awake, maybe while they're asleep, they dream about what their parents do. And then they play house with other kids. And then they can tell you, this is what a mommy is and this is what a daddy is. Wouldn't it make sense that our language would develop in the same way where, okay, we have a novel experience, then I'm acting the thing out dramatically, like, here, like, here's the drama, here's the stage, I'm going to hold this thing in front of you, this is what it is. And then I can represent it in the abstract with a symbol, like, that's enough.
Mm-hmm.
Okay, we have an assignment of an identifier. And then I can create narratives, like I can speak dramatically using my low level concrete vocabulary so that I can say Marino wanted to get a job in cybersecurity and he had to do all of this work and he had to learn all of these things. And he faced this gigantic challenge. Like day after day, he would wake up and he would do battle with it. And sometimes he would lose, but eventually he persisted and he achieved victory over that thing. Like Marino's a fighter. I'm using metaphors to describe an abstract problem. Like maybe I could say it more abstractly, like you wanted a job that required capabilities, that required knowledge that you didn't possess. Time to go.
Ready.
All
Yeah.
right. All right.
We got into the heat of things always, but this was such a great conversation. On my mind, it's
Well,
spinning.
cool, good. And now, man, you have helped me out a lot because I think I might be able to shoot a video now and using the answer that you've given me and the research that I've done, and I might be able to be done with my work for the week by 6 p.m. and then watch a movie with my wife instead of staying up until midnight. So thank you.
Yeah, no, of course. I had a different understanding of what this was going to be, the way that you asked. But I'm glad I was able to help. I thought it was more like an actual technical, like, hey, I have like Python 3.19 and I'm trying to like run it in this VM and I don't know how to like get the data in there in an efficient way.
I'll have one of those for you before long.
Yeah, please don't, because I'll be with you on Stack Overflow looking for answers.
All right, man. Yeah, it was fun. Let's talk about transistors sometime soon.